Hey guys, back again, talking about more kinetic stuff. This time we're going to go into differential rate laws. There's two types of things you can think about when it comes to kinetics. You have the differential rate law and the integrated rate law. These are two separate things that we're going to be talking about. It's pretty straightforward. Differential rate law is basically how does concentration change the rate? Okay, concentration and rate, how do they relate to one another? And then integrated rate law is concentration and time. So, for example, if I wanted to know how the rate changes based on the concentration, I'd use the differential rate law. And if I wanted to know 300 seconds from now what's the concentration, I would use the integrated rate law. All right, cool. So, those are two separate questions. And what I'm going to talk about today is this differential rate law. Basically, how does the concentration change the rate? So first off, does the concentration of your reactants and products change the rate? Yes. Yes, it does. You might remember this figure from the last lecture. Let's kind of look at this here. With this NO2, nitrogen dioxide, for 100 seconds, we gained 0.0037 molar. Okay, and that's at time 300 to 400. Okay, as we move forward and gain more and more and more at a different concentration of nitrogen dioxide, it changes the rate. This slope is different. This, we have the same 100 seconds, but the change is less. Okay? And that's because the only thing that's different here as here is that we just have more nitrogen dioxide. We have a higher concentration here. If we go down to very low concentrations, where we start with 0, this 100 seconds, we see the same 100 seconds, but a much greater change in concentration. So the rate is much higher down here than it is in the middle, and over here where we have a lot of NO2, it's even less. So the concentration most definitely does change the rate. The more product you have, the slower the reaction is. The more reactant you have, the faster the reaction goes. So we do see that there are going to be changes here. We can mess around with these concentrations and see how it changes the reaction. Now there are going to be some concentrations where you change the concentration and it doesn't change the reaction rate at all. It doesn't change the speed. You can have a lot, you can have a little, doesn't change the speed at all. Others messes around with it a little bit, others mess around with it a lot. And what we call, and we can see that based on something called the rate law. This is just kind of a mathematical way of thinking about things. So we have our rate, or the reaction rate, total reaction rate here. And there's going to be some constant, K, little, and this is going to be, I'm going to be very specific here. This is little k. This is the rate constant. Little k, rate constant. I'm making a big deal about it now because later on we're going to be talking about big K, and that's a different thing. This is little k. Little k, rate constant. Later on we'll talk about big K. This is little k. Little k is rate constant. All right, so little k is rate constant. This is kind of like the like E when we're talking about Beer's law. It's just going to be a number which is specific to this reaction, and not only that, but we're also going to say it's specific to a temperature. So same temperature, same reaction, it's going to have the same K. All right, so there's that. Then you have your concentration of your reactant. That's going to be part of the rate as well. Okay? And then you're going to have this N. N is what we call the order of the reaction. Okay, so this is going to be, can be to the first power, to the 0th power, to the second power, to the third power, something. It's going to show how much this concentration is going to change the rate. Okay. So you can imagine, what is something to the 0th power? Think about anything to the 0th power. Let's say we have 1,000. And if it's to the 0th power, what does that mean? Well, it's 0. Or, I'm sorry, not 0. It's 1. So it doesn't matter what we put here. If this is 0, it doesn't change the rate at all. Okay, think about this. If we have this and this is to the 1st power. So if I have 200 molar of something to the 1st power, okay, and then I change this to 220 to the 1st power. I raised it by 20. Okay. But what if I did this? What if I did 200 and then 220? Whoop. But I had this as to the 2nd power. This is a much greater difference, right? So the bigger this number is, the more the concentration changes the rate. 0, it doesn't change at all. 1, it changes a little bit. 2, it changes quite a bit. So there's that. Okay. So you can even see here, how does this change? If we look at the rate of the reaction here and the concentration, if I increase the concentration, how does it change the rate of the reaction? And if it's 0th power, it doesn't change the rate at all. It stays the same. Doesn't matter what the concentration is, it's the same rate. But if it's the 1st power, it is going to change the rate of reaction, and it's going to change in a linear fashion. I double it, it's going to double the rate. All right. Now, if I look at to the 2nd power, if I double the rate, or if I double the concentration of A to the 2nd power, I'm going to actually quadruple the rate. If I triple the concentration of A, I'm going to raise the rate, or I'm going to increase the rate times 9. Okay. If I quadruple A, I'm going to raise the rate by times 16. So it changes quite a bit when you have to the 2nd power there. All right. All right. This is exactly what we just talked about. 0, it doesn't change at all. A, it changes in a linear fashion. If I triple A, if I double A, doubles the rate. If I triple A, triples the rate. If I quadruple A, it quadruples the rate. Here, if I double A, I'm going to quadruple the rate. If I triple A, I'm going to multiply the rate times 9. If I quadruple A, I'm going to multiply the rate by 16. All right. So that's the difference there. Okay. Now, there's a phrase that we use, and that's called this is all fine and dandy whenever we just have one reactant. If we have one reactant, that's fine. But a lot of time we don't have one reactant. We have a lot of reactants. Okay? And you can have, let's say we have this general reaction, A plus B goes to C plus D. These smaller case letters here are their coefficients. Okay? And the rate law is just going to be the reactants. The rate equals K, again, that constant, times each of the reactants raised to some power. Now, we don't know what these powers are just from the balanced equation. The reason why I put these small numbers in there for the coefficients is to let you know those coefficients mean nothing in this rate law. They mean nothing in this rate law. All right? That is not how this works. This is a very common mistake that a lot of people use. They think the coefficient goes into the rate law. It does not. It does not. You have to figure out these exponents experimentally, and I'll talk about that at the later on. All right. So when we talk about the total order of this reaction, it's pretty easy. All you have to do is just add the exponents together. Okay, let's give you an example here. Okay, so let's say we have this really complicated redox reaction here. Okay, this redox reaction, here it is. It's already balanced for you, so you don't have to go through that headache. And experimentally, we found this to be the following rate law. We found the rate to be K. Again, that's going to be just some sort of constant. Then the bromide ions to the first power. The bromate ions to the first power. And these hydrogen ions to the second power. All right. So what we can say here is that this reaction is first order in relation to the bromide ion, this guy. This is first order in relation to the bromate, BrO3 minus. And this is second order in relation to the hydrogen ions. Okay. This entire reaction is 1, 2, 3, 4, fourth order. We add the exponents together, and we say that this is a fourth order reaction. Okay. We all good there? If that didn't make sense, you can ask me about it next time we see each other. So, again, what is the order of each of the reaction species? So this is going to be first order for bromide, first order for bromate, second order for the hydrogen ions. And the total order is going to be fourth order. 1, 2, 3, 4. Okay. What does that mean? It means that if I were to double the bromide ions, how would that change the rate? If I kept everything else the same and I doubled the bromide ions, how would it change? Well, if I doubled it, it should double the rate. Okay? If I doubled the bromate ions and kept everything else the same, what would happen? Well, I should have doubled the rate. And if I doubled the hydrogen ions here, what should happen? Well, if I doubled it, double to the second power is quadruple, so I should multiply the rate times 4. I should quadruple it. You see? That's what we mean here. Now, when we talk about the entire reaction together, it's to the fourth order because we add all of these together. So again, what happens if I double this? Well, I should double the rate. Now, what happens if I increase the pH by 1? Now, this is this is kind of adding in that acid-base stuff from before. What does it mean to increase pH by 1? Well, if I increase the pH by 1, what I'm really doing is doing base 10, right? So if I'm increasing the pH by 1, I am decreasing, I'm decreasing hydrogen ions because I'm getting a higher pH. And if I'm decreasing pH by 1, that means I'm decreasing the concentration of hydrogen ions by a factor of 10. And then if I'm quadrupling that, I'm decreasing this by a factor of 100 because 10 squared is 100. So there's that. This is kind of adding in the acid-base chemistry to this as well. All right. Next thing is different units of K for different orders. Units must equal out dimensional analysis, right? So we know that rate is always going to be molarity over seconds. So that means that the K is actually going to change things around a little bit, right? What units will K have in a 0th order reaction? So if it's a 0th order reaction, that means, molarity molarity to the 0th power is just 1. There's no units left. So that means K has to be, the units of K has to be molar per second to make sure that these are equal. The same units on both sides, right? Here, in a first order reaction, it has to equal out to molar per second, because that's what a rate is. But the concentration to the first power, you're just going to have molar, which means we need to have 1 over seconds on bottom for K, in order to get this out. So the units for K in a first order reaction is 1 over seconds. Okay, now for a second order reaction, you have, again, still have to get molar per second, but now we have 2 molars because this is molarity to the second power, so it's molar squared. I have to get rid of one of these molars. So that means that nothing on top and then a molar seconds on bottom. It's going to show you what I mean. Imagine if you had molar times molar, and I am, again, trying to get molar over seconds. I'm trying to make this equal out. What do I need to put here? Well, I need to cancel out one of the molars, and then I need to put molars on second, molars and seconds on bottom. So now I have molars per second. That. All right. So there's that. Sometimes you can just, if they give you K and they give you units for K, you can just immediately tell, oh, this is what the order of the reaction is. I can tell because the units of K that they gave me. All right, one last thing. Let's go through and actually experimentally determine the order of the reaction. How are we going to do that? Well, like I said before, if I double something in its first order, what's going to happen to the rate? It's going to double. If I double something in its second order, what's going to happen? It's going to quadruple. 2 to the second power. What's going to happen if I double something and it's the 0th power? It's going to stay the same. Okay? So we can use that. We can do, let's just look at this first example here. Okay? We're going to run 3 separate trials. I'm going to have one where the concentrations are the same, and I'm going to get a rate. For trial 2, I'm going to take one of them, and I'm going to double this. So this here, A stays the same, but B, I'm going to double the concentration. I doubled the concentration of B. So that means that I should be able to tell if it's 0th order, nothing happens to the rate. If it's first order, it's going to double as well. If it's second order, it's going to quadruple. So what happens to the rate? I double B, nothing happens to the rate, which means B is 0th order. Okay? I change concentration of B, nothing happens to the rate. Now, let's do the same experiment, but with A. So I'm going to look at 1 and 3 now. Keeping B the same, but what am I doing here? I'm tripling the concentration of A. I'm taking 0.1, now it's 0.3. I'm tripling A, which means that if it's first order, or if it's 0th order, nothing happens to the rate. If it's first order, it's going to triple the rate. If it's second order, it's going to multiply the rate by 9. So let's take a look. The rate, what happens here? It triples the rate. Since it tripled the rate, we know that A is first order. So if I wanted to write the rate law, we know rate equals K, concentration of A to the first order, then concentration of B to the 0th order. Now, a lot of times, if you see something to the 0th order, you can just say it's 1 and just ignore it. It's not there. If you guys write it, it's fine by me. But just remember that sometimes they'll just leave this off because this equals 1. Concentration of B to the 0th power is 1. All right. So then what's the total order for example 1? It's a first order reaction total. It's first order in relation to A, and it's 0th order in relation to B. All right, we can do the same thing here. All right, so let's do example 2 now. I'm keeping A the same, and I'm tripling B. And what happens here? 2 and then 54. What does that actually turn out to be? I need my calculator. So 54 divided by 2, 27. That can't be right. So I'm tripling. What is Oh, 27. The third power. So here we know B is to the third power. I'm tripling this. So what's 3 cubed? What does that turn out to be? 3. Where's the cubed button? There is no cube button. And it's 3 times 3 times 3. 27. There we go. Yeah. Yep. Okay. So we know that the concentration of, or the B is to the third power. It's third order in relation to B. Now let's see what happens here. Now I'm going from here to here, 0.1 to 0.15. What am I doing here? I'm not doubling it. This is, to the 1.5. Right? I'm 1.5ing it, multiplying it by 1.5. So then here, this should be going up by 1.5 as well. What is this going up by? It's going up by 2.25, which I believe is 1.5. Yep. The squared is 2.25. So then that means that we have the concentration of A squared. Burp, burp, burp. So, and again, K, rate. Here's the rate law for example 2. It is second order in relation to A, third order in relation to B, and the entire thing is fifth order. All right. And that's that. This lecture is getting a little bit long, so I'm going to stop it here. But that is how we go about getting, determining the rate order. All right, guys. See you guys.